China has, in the past few decades, seen an unprecedented level of growth, driven largely by its industrial sector. This has allowed the government to invest heavily into infrastructure projects, both domestically and abroad. Now, authorities are beginning to look at what lies beneath the ground. Keep watching. We're going to find out why China's drilling the deepest holes. Let's look at some of the reasons for digging deep into the Earth. So, super deep boreholes. They're one of the most complex projects in the field of geosciences. They're often drilled to depths of more than 30,000 feet, or about 10,000 meters, and they're important ways to explore the Earth's interior. There are a number of reasons to dig so far into the crust, ranging from scientific exploration or resource extraction to environmental monitoring and technological advancement. They are, of course, extremely useful for further understanding the Earth's structure, as virtually everything we know about the planet we call home is based on inference and not by direct observation. By drilling deep into the Earth's crust, scientists can obtain samples and data that teach us when to run out. Companies and governments are increasingly turning to deeper layers of the Earth to find new deposits. It's not just about traditional energy either. They too can help in geothermal energy, which is a renewable energy source. In areas with high geothermal gradients such as Iceland and parts of East Africa, super deep drilling can access the Earth's internal heat, which could be used for power generation and heating. There's also a role to play in environmental monitoring and understanding climate change. One of the most important uses of deep drilling is the study of past climates, or paleoclimatology. And by drilling through layers of sediment, scientists can obtain ice cores and sediment cores that contain information about the Earth's climate millions of years ago. This could potentially also lead to new ways of reducing our environmental impact, such as with carbon capture and storage projects that involve injecting carbon dioxide deep underground into geological formations to prevent its release into the atmosphere. Monitoring these deep reservoirs is key for ensuring advanced drilling technology. Digging to extreme depths in challenging environments, whether in deserts, polar regions, or even the deep ocean, requires new engineering solutions, and the resulting technological advancements in drilling rigs, drill bits, and support infrastructure can be beneficial across the industry. Due to the extreme costs involved, though, much of what they learn in terms of technology, available resources, and plenty more has remained a closely guarded secret. And in the absence of sharing this information, China has little choice but to do it too, if they want to benefit from what can be learned. Still, to understand why China is embarking on this initiative, it's important to understand where similar things have been done before. Let's take a look at some of the deepest holes on the planet. The Kola Super Deep Borehole in Russia. The Kola Super Deep Borehole, which is on the Kola Peninsula in Russia, is actually a series of 5 holes, branching off from a central core, with one of them being, by quite some margin, the deepest borehole ever created. Reaching an incredible depth was far from simple, and it required the use of cutting-edge instruments and a great deal of perseverance to overcome the seemingly endless problems they encountered. As the drill went deeper into the Earth, a team encountered extreme heat, with the temperatures at the bottom of the hole reaching 350 degrees Fahrenheit, or about 180 degrees Celsius, which was 80% more than what had originally been expected. With the drill bits melting in the heat, this was one of the main reasons the project was ended. As well as the heat, the immense pressure down there was also far beyond what had been expected. The equipment had to withstand both the physical stress being put on it by the layers of rock around it and the mechanical challenges of drilling into unknown geological formations. The drilling process, though, took place over many years, with progress slowing down as the team encountered unexpected difficulties. Early on, things went relatively smoothly, but as they reached the deeper levels, it all became monumental and a hugely costly challenge. By the mid-1980s, the team was progressing at a rate of only a few feet, where it was not previously believed to be existing, suggesting a fluid movement deep within the Earth is much more active than had been realized. This borehole also provides insights on how tectonic plates move and interact, shedding light on seismic processes and helping to refine earthquake models. When the project ended, and amidst stories of strange sounds that could be heard from the borehole, it was sealed at the surface and virtually forgotten about. How about the Bertha Rogers borehole in the US? So the Bertha Rogers borehole was a huge deep drilling project that was undertaken by the US in the 1970s. In Oklahoma in the United States, and it remains the deepest borehole ever drilled in the country, reaching a depth of 31,441 feet, or 9,583 meters. The borehole was drilled by the Lone Star Producing Company in search of natural gas, and was targeting deeper reservoirs in one of the most hydrocarbon-rich areas of the United States. Work on the hull began in '72, and it took more than a year to complete, ultimately led to the abandonment of the well. Technologically, the Bertha Rogers borehole pushed the boundaries of what was possible in deep drilling at the time, and it highlighted the significant engineering challenge that are involved in deep drilling. The project set a benchmark for further deep drilling efforts in the oil and gas industry, which continue to explore deeper and more technically challenging reservoirs as the demand for resources grow. Possibly the main legacy of this hole, though, was to show that the crust of the planet is far more unpredictable than had been realized, and that the predictive models for what would be found down there were nowhere near effective enough. The discovery of molten sulfur was a particular surprise, and as technological advancements allow for more boreholes to be dug around the world, it's going to make you wonder what will be found next. The Sakhalin-1 project. The Sakhalin-1 project, which is on the northeastern coast of Sakhalin Island in Russia, is one of the largest and most complex oil and gas development projects in the world. The project's managed by a subsidiary of ExxonMobil. This drilling allows operators to tap into oil and gas reserves beneath the Sea of Okhotsk from the onshore drilling platforms. But of course, it doesn't mean boreholes reach as deep into the crust as other projects have managed. Sakhalin-1 is in one of the most challenging environments in the world, though, where harsh weather conditions, including severe winters, strong winds, and ice, make working there particularly difficult. The extracted gas here is transported through pipelines, which supplies gas to the Russian Far East and facilitates exports. In addition to its technical achievements, the project has shown how well-planned boreholes like it can have a significant economic impact, while setting high standards for environmental protection. SAFAD in the United States. The San Andreas Fault Observatory at Depth, or SAFAD for short, is a hugely important project that was set up to study the San Andreas Fault. Located near Parkfield, California, the project began in 2002, and it's part of the EarthScope initiative, which was designed to better understand fault and are released during tectonic events. SAFAD has also produced a unique opportunity to analyze the rocks and material inside an active fault, as core samples were retrieved from the borehole for detailed examination during its construction. The data collected has already led to a number of important discoveries. For example, scientists have found that the fault zone contains serpentinite, which is a type of rock that's known to reduce friction, and may help to explain why the San Andreas Fault is able to slip more easily in some areas. Further to this, findings have improved the understanding of the relationship between fluids and seismic activity, finding that fluid pressure can play a significant role in fault movement and the formation of earthquakes. From a technical perspective, SAFAD was a hugely challenging project. Drilling into an active fault zone presented risks such as the potential for triggering seismic events, as well as difficulties in maintaining the integrity of the borehole. Advanced technologies and instruments were needed to successfully complete the project, including high-precision sensors that are capable of withstanding the extreme conditions. It still became one of the deepest boreholes ever drilled in continental Europe. This was a purely scientific pursuit to look at the physical and chemical properties of the Earth's crust, especially in terms of seismic activity and tectonic movement. By drilling into the crust, scientists wanted to further understand how heat, pressure, and fluid movement interacted in deeper rock formations. One of the most important and surprising finds of this project was the discovery of an unexpectedly high heat flow at greater depths. Temperatures rose to 509 degrees Fahrenheit or 265 degrees Celsius at the deepest point, far greater than had initially been expected, even with data from other boreholes. Another important finding was the discovery of fluid-filled cracks deep within the crust, which was a new phenomenon that overturned earlier models that assumed rocks at depth like those were dry and rigid. The fluids found in these fractures could influence rock behavior under stress, potentially contributing to the movement of tectonic plates and the generation of seismic activity. Drilling through too much to overcome, and the project came to an end. But while the KTB borehole did not reach its initially planned depth, it was considered a success for the data that it generated. Let's take a look at the Siljan Ring boreholes in Sweden. The Siljan Ring boreholes in Sweden are part of a unique geological and drilling project that explored a deep impact crater known as the Siljan Ring, which had been formed by a meteorite collision over 300 million years ago. Located in central Sweden, the Siljan Ring is the largest impact crater in Europe at more than 32 miles or 52 kilometers in diameter. The borehole drilling began in the 1980s as part of an effort to search for hydrocarbon reserves. As a result of the idea that the impact craters could host valuable oil and gas deposits. But it was also of huge scientific interest to learn more about what happens during a large impact like this. The drilling here faced a number of technical challenges, though, and proved to be far more difficult than what it's like to drill elsewhere. The complexity of the fractured rock layers, combined with the difficulty of navigating through the layers that had been... During the drilling, scientists found evidence of microbial activity at great depth, raising questions about the limits of life on Earth, and showing that no matter how inhospitable a place may seem, life, often finds a way. The Krafla Magma Drilling Project in Iceland, which is in northern Iceland, is a leading geothermal energy initiative that was developed to study magma and its potential as a direct energy source. Beginning in 2009, it involved drilling into a magma chamber that's almost 7,000 feet or 2,100 meters below the surface near the Krafla volcano, which is a highly geothermically active region. While geothermal power is already an important energy source in Iceland, the Krafla Magma Drilling Project looked to take advantage of much higher temperatures than those that are usually reached in normal geothermal wells. During the drilling process, the team encountered magma at a depth much shallower than they had expected, which provided a rare opportunity for scientists to study the magma directly. The drill hit molten rock at between 1,600 to 18. By studying the physical and chemical properties of the magma, scientists learned more about volcanic behavior that could improve volcano monitoring and prediction techniques. The data gathered here also has been valuable for earthquake research, as the high-pressure conditions near magma chambers can influence seismic activity, and studying this relationship can help improve hazard assessments in geothermally and volcanically active regions. Okay, let's check out Project Mohole. Project Mohole was an American scientific initiative in the late 1950s and early 60s, which aimed to drill through the Earth's crust to reach the Morohovicek discontinuity, which is more commonly known as the MOHO. It's of interest because it's a boundary located several miles below the Earth's surface that separates the Earth's crust from the mantle. Named after the seismologist who first proved its existence, the project was part of an effort to study Earth's deeper layers and improve our understanding of its composition and the processes that take place within it. The project was originally put forward by the American Miscellaneous Society and was 3,600 meters of water. This was a major achievement for its time as the deepest underwater drilling project to that point, meaning the project had already proved that deep-sea drilling was possible. But this early success wouldn't continue. Project Mohole soon began to face technical challenges. Deep-sea drilling at such extreme depths required cutting-edge technology, much of which had to be developed specifically for this project. The costs here began to spiral out of control, leading to budget overruns that strained the government's support. By 1966, with increasing skepticism and political pressure, Project Mohole was officially canceled. The techniques and technologies, though, developed for the project, such as dynamic positioning systems to stabilize drilling platforms, became fundamental to later ocean drilling programs, and the project directly inspired the creation of the Deep-Sea Drilling Project. Alright, so let's see what boreholes have taught us so far. There's no doubt that there's a lot that's remained classified from some of the more ambitious variations in the density and porosity of the rock. The KTB borehole in Germany also offered new information on the physical properties of deep rock formations, and scientists discovered that the crust contains fluids at far greater depths than had been expected. Additionally, temperature and pressure at great depths. It was predicted before anyone dug deep into the ground that they would experience high temperatures and pressures, but it turned out to be far more extreme than anyone had thought. The temperature at the bottom of the Kolar super-deep borehole, for example, reached 356 degrees Fahrenheit or 180 degrees Celsius, which was far higher than expected at those depths. This discovery provided new information about the geothermal gradient, and it's vital for understanding the Earth's thermal dynamics and volcanic activity. Insights into tectonic activity and seismic processes was another one. Findings from these super-deep boreholes have greatly improved our understanding of tectonic activity and seismic processes. By influencing the mechanical properties of rocks, the fluids down there may extreme conditions of the heat, pressure, and darkness. These deep biospheres have made scientists rethink the spread of life across the planet and raises interesting questions about what else may live deep beneath our feet, as well as the potential for life in similar extreme environments. With so much having been found already, and so much more to reveal, it's no surprise then that China has decided to proceed with super-deep borehole projects, with the potential to make some truly new, groundbreaking scientific discoveries. Now, what about China's current projects? The Tarim Basin Borehole. The biggest major drilling project in China at the moment is the Tarim Basin Borehole, which is a major deep earth exploration program in the vast Tarim Basin, which is in the desert of northwest China's Uyghur Autonomous Region. With a planned depth of 36,417 feet or 11,100 meters, it is one of the deepest ever attempted. The main intention of this borehole is scientific exploration, using the latest technology to study the structure and composition of the Earth to exceed 130 megapascals, which is around 1,300 times what we experience at the surface. Still, the drilling process is expected to use up a large number of drill bits and require over 1,000 drill pipes, showing just how ambitious this project is. Amazingly, after starting in late May of 2023, the borehole has already reached a depth of more than 33,000 feet or 10,000 meters, having gone through 13 continental strata, and is already using more than 1,000 drill pipes and over 20 drill bits. According to engineers on the project, progress is going to slow down rapidly from this point as they continue to head towards the goal, as the drill pipes have begun to behave like cooked noodles. They're extremely difficult to control at anything other than extremely slow speeds. Let's look at the Sichuan Basin borehole. Well, the Sichuan Basin borehole is another ambitious and technologically advanced drilling project in China that is, again, designed to explore deep geological formations. Now, the main reason for digging a hole here is to explore and extract deep